this next session I'm really excited about, and I'm just going to introduce very briefly, is the notion of grafting, is the role of interbody materials in creating a fusion, and also bone graft choices. Again, an area where there's a lot of variation. And we're going to start off with Keith Poelstra. Keith is coming to us from Las Vegas. Keith is a good friend and a colleague who's trained as an orthopedic surgeon, but has certificates in both orthopedic surgery and neurosurgery. He's recognized as an expert in bone graft materials, in material sciences, as well as in use of robotics.
Thanks so much. So on the topic of prone lateral, I actually started doing prone lateral when I was in Baltimore in 2005 when I started out of my fellowship. And the only reasons I've done it now, or I do it now, is people that have adjacent segment disease. And, you know, sometimes people develop this, like, horrible vacuum disc phenomenon. I'm not sure what that is. It's like there's osteonecrosis of that vertebral body of L4 or L3 where the prior fusion stopped, right? And they develop this, like, really sclerotic end plate at that adjacent level, both above and below. They get this vacuum disc. And if you lay them on, like, a table with a bolster under their back, that sort of degenerative spondylolisthesis with rock-hard bone opens up widely. And you get a CT scan and you see this big vacuum disc in there. Putting those people prone helps to reduce that spondy, and then you put like a 12-degree lordotic lateral cage in there, and whether it is the, what is that thing called? Like the prone duo? Where's Pierce? That's like this expandable mesh, you know, that's like being touted now as the thing against the PTP from ATEC. Or you just use your regular lateral cage. I mean, that's the indication to do it. And I do maybe 1 or 2 a month, so I do a dozen a year or so. But for the past, you know, so many years, I've done about 100 of those. That's, I think, where it helps me. It doesn't speed us up per se. That's not the reason. But I think the positioning helps you to position those two pieces of vertebral body in a better position. And then the prone lateral makes a difference. Anyway, we talk about interbody material, which to choose. I mean, this is sort of a, you know, discussion again about whatever works for you is best, right? So this is in Kuala Lumpur. I was giving a talk there, and this is we don't have audio, unfortunately. But this is a piece of 3D printed titanium, I think. But this is how spine care is being performed elsewhere, right? While we are like thinking about, you know, what kind of, you know, interbody do we use and how we're gonna, I mean, this man was like intermittently screaming. He's holding his hand, I think you see, right in front of his face. But this is how spine care goes elsewhere. And we're thinking about, exactly, right? Exactly. That's the low special this week, you know? So I thought it was, and this went on for like, you know, half an hour on one patient, and they were lining up for this chiropractic type procedure. He rolled out his little mat in the mall, and that's where he was treating his patients. You see the fan going there, right? Because he's obviously working hard. Anyway, so what are we talking about? These are my disclosures. Right, exactly. Black and blue by the time you're done. Anyway, so we're talking about this patient, right? So you do an interbody, and this is the early days, and you put a PEEK cage in there, and this patient gets screws, and patient's doing fantastic. And then he has a, you know, some kind of abdominal pain. He gets an abdominal CT scan. You extract the CT from this. And you're kind of embarrassed to see, but this patient's doing fantastic. And we have all of us have seen these patients, right? So is this really about fusion, or is this about sort of the right kind of stability? In the long run, this might not fare well, right? But everybody knows that sometimes, despite what we're trying to do, getting beautiful interbody fixation and on-growth to cages and so on, that sometimes these people do really, really well, despite when you get this out, there's just this fibrous band or so in there that hasn't done anything for creating a true fusion. But again, on the patient-reported outcomes, they might actually do really well. So what is this about, right? Interbody fusion, we talked about this earlier, 1947 or so is when this was early described. We had allograft, we had femoral rings, things have come and gone, and that means that if there's a lot of developments, right, that nothing must have been perfect, otherwise we would have stuck with it. The ideal interbody device, I think everybody agrees, whether you go from the front, the side, you know, whatever it is. I'm a flip surgeon, meaning functional lumbar interbody procedure. Whether you do it from the front, from the back, from the side, whether you flip them or not, it needs to be easy to insert. It helps to create the spinal balance we need. It needs to get height. It needs to help in your decompression. It shouldn't subside into the bone or anteriorly, not like that. And ideally, it carries some bone in, out, around, through it. And it may help the fusion process in an ideal scenario, right? So putting a hydrophobic thing in there. People remember the stacks cages. People are still using that, I think. There's no bone in it at all, right? You just stack up this plastic and it comes across some way. I think that's not ideal. But then again, the modulus of elasticity of that construct was relatively good. So sometimes these people do really well. And then ideally, you also see if the bone actually grows through it, right? So this is a tall order for things to be met. We know that certain implants, and there's a lot of studies on this, and I don't want to belabor it, create more of an inflammatory response. So this is the macrophage type 1 instead of 2, and I'm really looking forward to Dr. Abjornson's talk because I think she's going to go deeper into this. But to help the fusion means that it probably should not be hydrophobic. It shouldn't push cells away. It should help to create less than 50 microns of motion because it shows that the osteoblastic cells that help us need less motion than that to be able to jump across. If there's a consistent motion greater than 50 microns, they just can't bridge that gap. There's all kinds of cells that should be attracted, and ideally we encourage them to make bone. It becomes integrated as this cage sort of evolves in the fusion mass, and I think due to good elasticity and porosity, if the cage can help with immediate stability, patients feel better. And people that have transitioned from a very slippery PEEK cage to maybe titanium with some hoops and things that are sort of like Velcro onto the bone, you've seen that within the first couple of days, these people do better than people that still slip and slide back and forth over the old PEEK cages. We want to have a biomechanically favorable material. And then if we have something we can look through, but then we start coding it, I mean, this didn't go so well early on either, right? Because people have seen all these sort of devices not do as favorable as possible. There are some porosities now that are more encouraging, I think, with a little subsidence, even if it's made out of this material to help your fusion process. But you want to be cautious in what you pick. If you have a 3D printed material, and I'm really excited about Dr. Henderson telling us about how these things are being made and what is actually better than certain other techniques. Just having a 3D printed structure doesn't mean that it's going to help your fusion, right? Because the middle part here shows a very slippery surface still, although it's out of titanium, and it might be a slightly more bioactive, encouraging the calcium phosphate to form than if you had PEEK. But if it has more valleys and hills and all that kind of stuff, actually the cells do a lot better. And we know from both macroscopic and the microscopic structure on these two devices that this actually is a more active surface that potentially can help you get things to fuse. And I'm really looking forward to the further development also for what's going to come out in the neck and over the next few years to help us with the fusion. So if we look at this and you get eventually good spinal balance, I think the balance is far more important than if the biomechanics are right. Whatever you put in those cages eventually is probably going to fuse with a plenty stability. But we know from PEEK that you have a lot of these sort of fibrous bands that can form. So if there's not enough inherent stability right away, the bone will not bridge across in the center, and around the PEEK itself, you get this sort of fibrous third body response because there is motion that potentially you would not see against the titanium cage. So that probably makes a little bit more sense. Despite all the excitement that there is over nanotechnology and so on, I think the mechanical stability out of the gate is key. And again, PEEK and even the carbon reinforced fibrous PEEK that we had for a while, it really has no surface benefit. And I've seen a lot of these cages that retrograde, especially with expanding mechanisms, go into the spinal canal. Whereas we know from total joints already that ingrowth helps, right? We had these plasma sprays roughening much earlier than we ever awoke to this in spine, and there's many other examples of sort of this tantalum. You remember all this from Apex Medical that then got bought by Zimmer and eventually was very successful. We had these blocks in the spine that you unfortunately couldn't see anything through, but you remember when you put them in, it's almost like Velcro, right? The soft tissue and the bone immediately very stable got onto it. And that's not just true for metals, but also for example, if we look at the phosphates that we use as bone graft, you see a product on the left-hand side. It is the same product as on the right-hand side, but the cells on the left side with that surface respond very differently than what you see on the right side. So changing the surface of the same material might actually have some benefit, and I'm really looking forward to Dr. Abjornson, her talk about seeing what bone cells can do when surface modifications of the same material are being applied. And we talk about this, that you have a macrophage 1 response to a surface that's unfavorable on the surface, and the same material, if you change it, you get a macrophage 2 response that actually can then lead to an osteogenetic response and actually that bone grow on that same material just simply from surface changes. So what do we look at? We look at porosity and pore size. There's a lot of science on this, what the porous structure of a titanium implant should be. Typically ideal is touted 65% porosity maybe. 500 to 600 micrometers, and then the beaded surfaces that we typically saw on joints already, just out of sheer luck because they could make them by hand, right? They put these little balls on there by hand, was about 250 to 400 micrometers. So that actually worked already. And then the way that you do these studies, and Bill Walsh is phenomenal at this, right? There's little holes that are being drilled. You can put a variety of implants in there. We've learned a lot from PEEK, titanium-coated PEEK, and so on, by push-out testing to see how well these things incorporate. And if you simply look at, the same little pegs placed in this case, a rabbit femur, you can see that titanium-coated versus regular PEEK has a big difference. It's the same material, basically. It's the same modulus of elasticity, but simply the response on the bioactive surface of titanium on the right-hand side there shows much better incorporation and a much better sort of bone quality interface with the implant. So if we consider PEEK, I think for a long time it was used and touted for the elasticity closer to bone, that it was better. But unless you put something large in there, this is what I usually started to do in the beginning when we started to use PEEK. It was very hard to get a stable union, and you saw a lot of these things with expandable cages that had still PEEK surfaces on the top and the bottom. That was maybe a good idea, but the expansion mechanism already prevented you from putting bone graft in there, and it simply did not lead to a solid fusion. So I never understood this part, right? That you had an expansion mechanism and then PEEK on the top and the bottom. So where could you really put the bone graft? There's no ability for the surface to adhere to bone, and there's no bone graft in there. But then I looked at some coronal recons, and I saw what this shape sort of was, and it reminded me like this is more like a dollar sign than anything else. So I think this was possibly the early reason why these expandable cages were created. So, so there is, with these inflammatory data out there, there's very little interest in this. So if I used them earlier, I always felt that, hey, the space in the interbody graft is so large, maybe I should put a big block of structural bone in there. So this was before 3D printed titanium was even available. And then what I did too is that I put a little plate on the front, and I usually used a bioresorbable material to reconstruct the ALL almost, if you will. So then when you hang the patient prone after an ALIF, you don't distract the front, but the ALL that is reconstructed with this becomes your fulcrum. So you actually compress against the cage, and biomechanically this made a lot of sense. So then as soon as 3D printed titanium came out, that seemed to be the holy grail for me. So that's what I've been using ever since probably 2010. The early data was promising. I like things that have a good bone graft chamber. The porosity should be optimized. I like to stuff these cages, and I think that the wall thickness, as opposed to what we saw with especially the carbon fiber reinforced cages that were really thin, the wall thickness, especially for laterals and ALIFs, helps a lot. And then that part of the cage becomes integrated in the fusion, and right out of the gate, patients feel greater stability with this. Same thing with this, there is the slightest amount potentially of intrusion, I don't want to call it subsidence, but intrusion of these hoops that you see into the end plate, and it contributes immediately to a tremendous amount of stability. And people that do a lot of surgery, you see how well these folks feel right when they get up the same day of surgery. When I did PEEK or other implants, I used sometimes, still the femoral ring allograft. These folks still hurt from a little micro motion against the cage. Once you put this in, it's sort of like a Velcro connection, and it immediately allows for excellent fixation. So I'm excited to learn more about how this process works. So Dr. Henderson is going to talk about that soon. And as you know, you can basically come up with like anything and everything nowadays. If you want to learn more, 3dprint.com is exciting. There's a lot of cool stuff on there if you're into like the 3D printing type stuff. And it is a fascinating technology, and you can print pretty much anything, right? And people that drive cars nowadays, they know that, all the stuff that's being made, even as, maybe early prototypes or final devices that you have in there, are created from a 3D print model. So talk about cases real quick. I think the anterior 3D printed implants are so good now that we can probably do less posterior going forward. You may need to have some, additional plating type techniques or other things to apply to the patient to be able to just get away with more anterior column surgery. But if we, I think, do a really good job balancing the spine, recreating the tension band in the back with lots of hardware is potentially not as much necessary anymore. So real quick, 78-year-old guy, obviously prior surgeries and all this. He needs to have a restacked spine and loss of lordosis and all this kind of stuff. So I like CT scans, right? And I never had CT scans in the past after I had an MRI on the patient already, but then I became interested in robotics, so we needed to get CT scans. I think the value is tremendous because you don't necessarily appreciate how bad basically the integrity of the spine is. So these people need stability, and I think if you do good stability in the front, no matter what you use, these folks are going to do well. You balance them well, and you put an implant in there that's going to support their vertebral bodies. And whether you do it just from front or back, or you do it from the side, I'll do a lot of these cases in older people with, olive or lateral approaches, and then drop the screws in from the side. And these people typically go home, about a week or so, or a day or so later. And for 2 weeks, they need some home health. And before, when we did these open surgeries and T-lifts and all that, I could not get people to do as well. So the way I think differently about surgery now here, you can see a guy who had prior surgery, dural tears. He had a 3-4 fusion because they cracked his facet joint during one of his prior surgeries. He stands like this, and this is another classic example of somebody who just falls into the disc space. You can see on the MRI scan, he's relatively straight there as opposed to when he stands up, so he falls into his vacuum discs. So I love to restack these people. He goes from here to that MRI scan, as you can see. So typically, I operate on Mondays, Wednesdays, and Fridays. On a Wednesday, I do like a 2-level A-lift, 2-level O-lift, or lateral, or whatever it may be, above and around that fusion. Then I get people up and walking. Everybody walks within 5 hours from surgery, whether I do standalone in the front first and then set them up for the second day or not. Then we get a CT scan. It's very helpful to be able to evaluate them for their EHL and anterior tibialis weakness, right? If that is all better, then you don't have to do a decompression on this, and I'm a strong believer in indirect decompression and stability. Plan it with the robot, put posterior screws in, relatively straightforward. And as you can see, what is the biggest difference in my practice now is that I basically ignore all the old hardware that's in there. So good anterior support, and then with this here, I basically went over the old hardware. I'm sorry, I can't point to it, but I basically plan it in a way that I don't have to hurt people like that. And it takes about 45 minutes to an hour to put in those screws. There you go. Okay, thank you. And you can ignore all of this, and it saves a tremendous amount of surgery with good anterior interbody support. I don't think you have to grab every single vertebral element. So this is what that looks like. Planning is very helpful. I won't go over all the details with this, but I think that this is key, and especially if we have a case like this. So I don't really know how to measure lordosis in this patient. She's 400 pounds. She's 32 years old now. She was 16 years old, had a scoliosis operation in Pensacola, fell in the hospital, fractured her spine at the end of the hardware. They put her in a brace and then in a body cast for 6 months. She basically stopped developing mentally, so she is a 32-year-old woman in or a 16-year-old girl in a 32-year-old woman's body. 400 pounds, minimal ambulator. The family lives in a trailer halfway up in Alabama. This was when I was in Florida. And doting around this girl. Once in a while, the rods poked out at the bottom of her spine, as you can see here, when she sat against the hard surface. So this is, exceedingly difficult. And I think you need a lot of oomph here, and I think the interbodies help a lot, along with the ability to plan these surgeries. So you can see the size of this patient. I decided to do a multi-level, lateral, O-lift, whatever you want to call it. I plate these things because then I can get people up, scan them, create the osteotomy, and I think there's a little video of how to do this. So then I just sort of do this hybrid technique now, but I can bank on good anterior column support, the osteotomy, bring the rods together, and then there's sort of a side connector. I think that's extremely helpful here to close down these osteotomy sites and get these people upright and get them home the third day after surgery with sort of a hybrid minimally invasive approach. So she goes from here to there, grows about 3 inches just from surgery by restacking her spine, I think aided by the implant technology that we have now, and overall, of course, standing much better. Within the first 6 months, she lost 100 pounds of weight. Suddenly is a lot more ambulatory, obviously, and doing really well. So, in short, I think what you need to do well, despite all the interbody options we have, you got to plan your case, what works best for you, use the technology that's currently available. But again, there's no substitute, despite all the exciting interbody technologies and approaches for doing a good operation, doing a good discectomy. But certainly the implants we have now are making the process a little bit better. We've learned a lot from the technology that was there in the past. I'm excited to see what is coming, excited to learn about the 3D printing technology. And I think that during the product fair, take a good look at these implants because they're a little different than some of the other 3D printed equipment that's out there, and use it to your advantage. So thank you very much.
I appreciate that introduction. I have to be honest here. You referred to me as a doctor. There's a show that was on the radio show a few years ago. It asked Dr. Science, and it starts with, I may not be a doctor, but I do have a master's degree. So, my background, I was director of additive manufacturing in Detroit for a company named Linear AMS, and at the time, we were the largest metal 3D printing service provider in the United States, which 10, maybe 8 years ago was an interesting claim. The industry was still searching around for the Holy Grail. I've heard you guys refer to your Holy Grail, but our Holy Grail was to do serial production, to do real production on a 3D printing machine. And quite frankly, we had 20 machines. We were running aluminum, titanium, cobalt, chrome, Inconel, miraging steel, stainless steel, and even copper parts. Copper is very difficult to weld. Do we have any welders in here? Does anybody weld in their garage? Oh, hey. Then you understand the process of melting metal and creating weld beads, and that's really what 3D printing of titanium is all about. We had a complete machine shop, CNC machines, wire, electrical discharge machines. CMM is an inspection machine, and white light scanning. Our markets were aerospace, defense, automotive, medical, gas and oil, energy, consumer goods, and agriculture. Our joke was, there's a guy named Rick who stars in the TV series Pawn Stars. He says at the beginning of the show, I can guarantee you one thing, I don't know what's going to come walking in that front door. One day we had the Jet Propulsion Lab show up, and they asked us to create this little box, the JPL. What's that box for? It's going to Mars. Well, what's it going to do on Mars? We can't tell you. It was the helicopter, the base. If you look at the helicopter on Mars, there's a rectangular base on it. We 3D printed that several years ago. So let me fast forward a little bit. I met Camberspine coming off a stage. I met Dan and Bob Morris, and they said, hey, we're going to get into this 3D printing of titanium implants. Would you help us walk the show? We want to figure out which machines we should buy. So I walked the show with them, and that led to a relationship that's now several years old. I think, how long have I known you, Dan? 6 years? 7 years? Yeah. And I helped them set up their supply chain with the service providers who do titanium 3D printing. And let me see which one. There we go. So by 2020, which was last year, the supply chain was running fine, everything was going well, and Camberspine's growing, and they said, it would really be nice to establish an additive manufacturing facility of our own. And so we headed down the road. We named the company Zyresic, which an ancient Greek scholar would know that it means, the word means razor sharp. It literally means a razor, a scalpel. And more figuratively, it means that we're sharp or we're keen, so it kind of has a double meaning. But we're differentiating ourselves in the supply industry. When you reach into that tray and you pick up that part, that implant, and you're going to put it into a patient, what's it all about? What got it to that point where you have it? So we set 3 goals for ourselves. Number 1, provide an implanted product in 2 weeks from order placement. Well, one of the problems is sometimes it takes several months to get an implant when they order it. Secondly, no minimum order quantity on production orders. Like if you need 1 part, Dan, to replace what's in the tray that the surgeon just used, we'll make 1 part for you. And number 3, using the latest advances in additive and subtractive manufacturing. It's a fast-moving technology out there, and it's not staying the same. The machines that made these parts 5 years ago are not the same ones that are making them now. So we have a unique competence in the 3D printing of low-volume, high-mix production medical implants. Oops. I'm messing this up totally. There we go. The machine up there on the left, well, let me just read the little word there. It says, when titanium is heated, it becomes highly reactive and readily combines with oxygen, nitrogen, hydrogen to form oxides. The absorption of these oxides will embrittle the weld. This potentially renders the weld and part useless. That's out of the metal press. Titanium rusts faster than any metal that I know. It oxidizes very quickly. So one of the very important things is you don't really want to weld rust to rust. You want to weld virgin titanium to virgin titanium. The machine in the upper left there is made by 3D Systems. It's called a DMP Flex 350. And it looks a little bit like a pressure chamber. Well, what it is a vacuum chamber. Inside that machine, the titanium is being welded, the titanium powder is being welded essentially in a vacuum. So there is no oxygen in there to contaminate the layer by layer welding that you're doing. So this minimizes the oxide embrittlement and the oxygen inclusions. The other thing is we have subtractive machining, which down in the lower left, I don't know if I can get the video to go, but there's a new technology that came out a few years ago, which is fascinating, and it's called fusion coolant supercritical CO2. And you see the carbon dioxide spitting out around the cutter there? What we're doing is we're cutting the edges of the implant to smooth it out, to get it to print and to spec. And what's very unique about this is it's not adding any oil that could have machine oil that could have contamination. And for those who study this, the machine oil is purported to hinder osseointegration. And secondarily, it could harbor bacteria, which could hide in the trabecular surface and very difficult for us to clean. So our theory was, why put oil on just to take it off? And a professor from the University of Michigan invented this fusion coolant system, and it's really starting to take over in the medical device business. So we also talk about, up on the left there, you see a plate full of parts. And to the left is the actual implants. Above the implant, above the implant, that's a machining lug. And what we do is we hold that into the CNC machine by that lug. And on the very top, you can see a flat plinth. And what that plinth does is it's the barcode label for knowing exactly which part that is, which build plate it was on, what position it was on the build plate, because the FDA really is concerned about traceability of your medical devices. And then on the right side of the plate, you see tensile test bars. This is a little bottle that we grow on the plate that allows us to store a sample of the titanium powder that this particular plate used. So in the future, we may end up in some sort of a situation with a lawsuit, perhaps, but at least we have available to us the actual chemistry of the material that was used in that exact build. So that's kind of what a build plate looks like. Software packages are getting a lot better, and there's some interesting advances recently in what we call our support structure. If you look down here, these little tiny needles come up and they hold the bottom of that part up in space while you're growing the part from the bottom to the top. And that allows us to have very good geometric definition of the part as it's grown. This strategy was not available 3 or 4 years ago. One thing that we do is we fingerprint every single part that we make with a white light scan, so that we have an inspection report on each part. So we can look at the dimensions, we can look at the shapes, we can look at the trabecular surface. And these machines, these blue light scanners are coming down in price, and they're also very quick. So we can do that synchronous with our normal assembly process. So in summary, we've put together a disruptive supply chain model, 2 weeks from procuring the implant with no minimum order quantity, using the latest manufacturing techniques. The beauty is the state-of-the-art technology will reduce risk and deliver safe, defect-free products.
Thank you very much. So everyone has seen this slide 1,000 times at 1,000 meetings about cells, matrix, and signal. And why we always talk about this with bone grafting is because this is what autograft has. And all of the efforts in bone grafting that I've spent over the last 25 years has been to mimic this secret sauce in order to help you with your bone fusions. And these osteoinductive, conductive, and osteogenic signals can come in a variety of different ways. And I think one of the things that I've learned over the years is it's not ideal bone graft that there's a holy grail, that there's only one product out there. It's more that you have to think about what you're trying to achieve and how to mix that for the situation that you're in. Because at the end of the day, the only thing that matters is that our cells like whatever you mix together, and they proliferate and migrate along that so that you get a nice fusion. So again, at the end of the day, this is all that we really care about. And as Dr. Poelstra pointed out, they can't jump. So if you don't have a good bone graft and give them a nice surface, they simply retreat and die. So most of the morning has been spent looking at how to stabilize your motion segment, how to optimize your load transfer. This is what most of the morning talks were on, and it's very important. This is what you guys do for a living. I have never done surgery on a human being, only on animals, but I understand and completely understand why this is the beginning of how we do surgery, is that we begin by trying to stabilize the segment. Then, as we saw Dr. Henderson just explained, we do the materials and try to optimize our materials, and we'll talk about that a little bit. And then what I think everything should be about is how picking your bone graft. So all of you just simply do the carpentry so that we can have the magic happen with the bone grafting. So as Keys pointed out, we've gotten to a point where we can make osteoequivalent type of modulus with titanium. For those of you that ever try to do a ray cage or BAK cage, they simply subsided in because they were so much, their modulus was so much higher, and they didn't work out very well. So then we had this whole millennium of PEEK, and as Dr. Poelstra pointed out, there's nothing good about PEEK. It's just simply that it exists. So what we've moved on to now is biomimetic properties. And really, I feel like we've hit the third sequence of what we can do by making structures that have conductivity so that our bone grafts aren't in it alone, that they actually have conductive surfaces that the cells can use as they migrate along to form new bone. This guided bone formation is what then allows our bone grafts to not solely be responsible for causing that bony fusion. And what we've seen over the years is now, as we were just seeing in the last talk, is that originally 3D printing came out, and whatever companies could 3D print, well, that's what you got. What we are working on now is trying to optimize that 3D print, look at the surface characteristics, find out that perfect marriage between microstructure and nanostructure in order to be able to make our cells have the best environment. Remember, just because you can see roughness or friction on your surface doesn't mean it's optimized for our bone cells. And again, it only matters what the cells think. So as we work on this to optimize the surface, and I've spoken to you many times on our work here at Canberra to work on that, now we're moving on to look at making the perfect marriage with bone grafting. Because at the end of the day, depending on your design, all you're really trying to do is optimize the ability for that bone graft to work in that structure. So some of the titanium prints have made me laugh because there's absolutely no way that you're ever going to accurately fill that first cage with bone graft and make it a good synergy. The second cage, I'm sure all of you have tried it. We've tried it many times. It's very hard to fill. It's very hard to fill. And what you see sometimes in these is that because everybody just pushes bone graft into them, you wind up with a donut hole in the middle. And so you have to have something that has a nice structure that you're able to really fill it with graft well. And the Spira has that type of structure. I bring this up because I think this is interesting. So what we've always seen is gap phenomenon. When you used PEEK cages in the top spacer, you see it's filled with traditional DBM. Well, traditional DBMs, when they came out in the late 90s, early 2000s, they had carriers in them, and some today still have carriers in them. And what happens is those carriers are gone within 48 hours. So then your DBM shrinks. And when that shrinks, what happens is you don't have good bony end-plate contact. And if you don't have bony end-plate contact, what you have, again, is shrinkage and cells can't jump. So we have to move on to fiber type of DBMs that have no carriers so that we maintain good bony contact with the end plates over time, because what that allows to happen then is that we get a nice fusion through the channel or in the implant. And that's really what we're going for. When you've ever pulled out a peak cage, and all of you have, what you realize is that column of bone in the middle was never great. And along the edges where you packed some along the side to kind of cheat, that came out okay. But really, it popped out in seconds. If you've ever tried to take out a titanium cage, you realize what bony integration really looks like. Our friends at the FDA did something this past year, and I just bring it up as a public announcement for all of you that haven't had the opportunity to hear this, is that they finally cracked down on grafting materials that were out in the market that had no homologous use. So those that came to you with fat-based products, placental tissue products, all of these type of things, if you've noticed, you haven't seen any of those people lately. And that's because the FDA gave them a warning that they could submit IDE trials or IND trials. Most of them, 99% of them, did not. Waited for the FDA to say, okay, we finally had enough. They finally had enough this year after COVID and cracked down. So homologous products now that's why you're seeing a return more, or when people show up to talk to you more, they're talking to you more about bone grafting again and talking to you about fiber products, stem cell products, because the FDA has said no more products that are not homologous use. So I wanted to start with Biogen. Biogen Bioactive is very similar to maybe something that you've seen in the past, which would be maybe like a VITAS Bioactive or any of the other type of products. It's a classic solid osteoconductive scaffold. It's a synthetic product. It's mostly beta tricalcium phosphate. It has bioglass on the surface and then mixes with collagen to give you good handling products. The interesting thing about Biogen is that it does take about twice as much liquid as VITAS. That's very important because you need to mix Biogen with something like either marrow or blood or a spin down of blood or marrow. And the reason that is that gives you back your osteogenic potential with your osteoconduction. These products are excellent. There is a need for synthetics. There are patients that you always worry about that have a very allergenic type of characteristics, and you're like, no, I have to use a synthetic, or for religious reasons, sometimes we have patients that do not want an allograft. So these make sense, and they're very good products. The excellent part about synthetics is that they hold their space. So if you have to use this in the gutters or different areas, you can always know that it'll hold its space well and that it will be there. This type of product resorbs in about 18 months, so it will resorb in a profile that works for bony integration and bone formation. Some of the earlier synthetics that maybe some of you tried and got burned on had a very quick resorption characteristic, whether or not bone actually had a chance to grow, and then you would wind up with a pseudo. They're very versatile with the collagen in them and make it easy to mix. Demineralized bone matrix, I always put up Marshall Urist's description and definition of a DBM, because this DBM is nothing that we ever see anymore. This mild extraction type of DBM that we see that he first described is nothing that we really have realistically in the market today. The FDA went back on DBMs in 2006 and decided to regulate them under a 510K process or a human tissue process. So one or the other today, but what that did was give us a lot more sterility, and a lot of what Marshall first explained is not exactly what we have today. But I think that one of the really interesting parts of the infill profile that is now here at Camber is that each of these products is verified for osteoinductivity versus having osteoinductive potential. One of the things that you've all learned over the years as people come into your office, and I sit on the bone banking committee at HSS, which is a tireless, horrible position to be in, is that when people come in and they want to put their new DBM in your hospital, you say, okay, how do I know it works? And they go, well, it has potential, it's a DBM. And you say, do you test it? No. Do you verify it in any way, in vitro, in vivo? No. But you know, a lot of them, I ask them simple questions. Where do your donors come from? Where are they processed in the U.S.? These are basic questions, AATB questions, but shocking to me how very little people know, because most DBMs these days are just a commodity product, and they feel that the surgeons don't care. But that's not true. You do care, because if you get a pseudo, you're the one that gets blamed. So the interesting part about the infill characteristics is that all of these products are verified for osteoinductive potential. Every lot is tested. It's tested in an athymic rat model, which is the I think is the gold standard of testing, meaning that every lot is tested to prove inductivity by the Edwards method. Gene Edwards published that probably in the late 90s. It's a 4-point test, but it allows you to know that donor is inductive. And they throw out any donors that do not meet an inductivity standard. And they also test for assurance of sterility out to 10 to the -6, which is very important for you to know, and was an FDA standard going forward on DBMs of this class. It's histologically demonstrated. What that means when you verify inductivity is that you see in that rat pouch model that you have new bone forming, you have bone marrow, you have osteocytes, you have chondrocytes, and you have cartilage. So if you don't see all these classic signs of new bone forming, then that does not get a score that allows it to be considered osteoinductive. I'm not going to go through this. I just wanted to point out that this is all tested in an independent lab, so it's not someone just saying, oh, our product's good, and then, oh, yeah, we tested it in our lab. Again, something you'll see often in a lot of these type of materials. This is all tested in an independent lab in the rat model as we described, and it's tested for 28 days and has to get a score of at least 1. It's a 4-point test, so 1 is perfectly fine for those of you that aren't familiar with the model. Infill then comes in many new forms. It comes as a matrix putty. That's great because it is irrigatable. The infill CFM is the one I have the most experience with. It's a fiber-based product. It mixes very well. This would be a lot like your OsteoStrand and a lot of the others. This packs very well in a spiral cage. And then you have the AFM, which is more of a material you would mix then with blood or marrow. I haven't used that one in the lab at all. And then the Crunch product, I actually was on the original Graft on Crunch team, and I really love Crunch type products. I think they work very well in the gutters. I think there's a lot of use for them to have a little pack. I think all of you that are used to packing with Autograft will understand Crunch and be able to use it. The strips and blocks, for some reason my picture, oh, there it is, comes up. A lot of you have probably used sponges, these types of products lately. They're great because they have a little bounce back. So if you fill them in, what you feel like is that they puff up when you add blood or marrow to them so that they keep good contact with your end plates. This product line is really an excellent product line and one of the very few that's actually verified for inductivity. So I think that you'll see that that's really important. One of the things we brought up earlier was, looking at your surfaces and understanding them, matching that with a product that will actually work. Makes your life as a surgeon much better. You slaved away in there for hours and hours, and if you would use inferior products at the end, it's really disappointing for you and the patient. Stem cell allografts, I'm sure all of you have seen these. They come around and you're never quite sure what they mean. They have cells, and I always think it's funny because when the person comes, I say to them, how many cells do you have? Because they all have a number. Oh, I have 250,000 cells. I have 140,000 cells. I go, what kind of cells? And somebody like Dr. Lieberman could quiz them down to the nth degree on that. And the answer is they don't really know. They just know they have cells. And I think that's funny and cute in a way, but it's sort of annoying that you're going to sell a premium product and you don't understand the cells that you have or why you have them, or if it's of any value for me to pay twice as much for it. In theory, they are the best of all the grafts that we have available, right? Because they have all 3 components that we started this talk with of cells, matrix, and signal. So one of the ways you can actually see if a stem cell allograft is worth actually having is, are the cells alive after they thaw out the product? One of the ways they always tell you is they've tested it before, and I say, well, that's great. That's not the product that I'm going to hand into a surgeon to use. I need to know after I've decanted them and thawed them and all the rest of them, that the cells are actually still alive. And the way that this is done is using a way of looking at viable cells as a live dead stain. This is a piece of actually Trinity that I had, and do a live dead stain after you've thawed it out. And I think that's very important, and one of the things that you have to ask the person that's handing you a stem cell allograft is, can I see the data that the cells survive your whole processing? Because it doesn't matter if the product going in was good, it only matters if the product going out is good. One of the things that I always thought was interesting about this class of products is understanding, why don't patients have a response to them? If you're leaving cells in, I always think of cells as, when I trained about bone grafting, as bad, right? Because the cells would have some sort of immune response. But one of the things that we understand about the processing of stem cell allografts is that they use an immune privileged type of a way of processing, so that they get rid of the HLA MHC antigens, meaning your histocompatibility antigens are gone, and therefore the patient won't react to them in a negative way. The MSCs also secrete cytokines to try to modulate this immune response. So in two ways we're getting rid of it. We're cleaning out the cells, the blood cells, the white blood cells, the red blood cells that would cause an immune response, and then also we're being able to provide cells that would basically promote bone fusion. The interesting thing about the infill CBM product is it's slightly different than Trinity or Osteocell or any of the others, in that it uses a two-step process. The first process, the uses sort of like uses sort of a shock treatment in order to clean the cancellous bone. By doing this, it gets rid of all the cells that you don't want there, your white blood cells, your red blood cells, and the other one. This osmotic type of shock then is able to clean out all the cellular components you don't want. In a second step, what's interesting is that they decant the cortical bone, and by doing this, they're able to get a slurry or a solution of growth factors. And then they marry this back together in order to optimize the type of cellular allograft that they're able to produce. This is unique to infill CBM. This is different than the processing that you usually see, where they simply wash out. This is a washout and an additive type of process, but it still forms a human tissue product. It's still considered minimally manipulated. It's available to be used. I think one of the things that's interesting about it is DMSO cryoprotectant free. For those of you that have had to go through that process with Vivigen, it is not the easiest thing in the world. It is available in a syringe and easy to use. I think the more important thing are some of the studies that have been done on it so far, is that we looked at 11 donors that they did to look at with just using the osmotic shock treatment, and then using the dual treatment of adding in the amping process with the cortical fiber solution. And what they see is, when they do the two-step process, that what you see is all the growth factors across the bottom that we usually look at in this type of process. And what you see is, by amping it up with doing the second step, is that's the percentage over the original process of just washing out. So it gives you a twofold process, and it shows that doing that second step is actually very worthwhile. And then looking at it in a posterior rabbit, they used a rat. You have to, because you have to use an athymic rat because you're using human tissue. They did a posterior lateral fusion study. This model is very well accepted. We use it all the time. And they looked at themselves against all of their competitors. And what they saw was that they had results very similar to Trinity in good bone volume forming, and a lot better than many of the competitors as far as bone volume. And then when they looked at bilateral fusion, doing manual palpation to show that the bone that they see is actually worthwhile, they saw, again, a very high response of manual palpation responses of that fusion mass. So what they know is that this product is performing well. We've all had bad experiences with these products. There have been other studies out. Huan Bei showed another study similar to this years ago showing low response with Osteocell and Vivigen. There was also another study out of Brian Frederick's lab last year, again, showing that this profile is very similar. So one of the things about cellular allografts is they're very new to the market, and processing does matter with these. If you're going to spend the extra money for a cellular allograft, understand that they're not all the same. It is not a commodity product, and you really need to understand the processing that's going into them to make them worthwhile for the money that you're paying for them. They're very widely used, obviously, in cervical, as BMP2 should not be used in cervical. So we try to really understand that we're processing and giving you the best product possible. In summary, what we're trying to do in all of our studies is support and enhance the repair that you guys have spent hours doing the carpentry for. Dr. Lieberman and I have shown over the years that these materials matter very much to getting rid of, say, your biofilm. At the end of the day, the biofilm that causes on PEEK and to a lesser degree on titanium can cause us all types of trouble. And when we try to override that by just simply packing a lot of grafting material, that doesn't always work. So you have to find the perfect synergy and formulation that's tailored to the procedure that you're trying to do and meets the obligations of what you're trying to do. And synergistically working between your hardware and your bone grafting really does take a lot of the burden off of not understanding, I did everything I could, I don't know why they didn't fuse. A lot of the times it's just simply the materials weren't optimal, and all your carpentry was wasted because the materials weren't perfect. Thank you so much, and enjoy your lunch.